In the last video, we took a look at the Doppler effect, and here we're going to finish up our treatment of mechanics by taking a look at self-interference of waves to make what are called standing waves. So to that end, we first have to think about what would happen if a wave reflects off of some sort of a boundary. So here I'm going to be thinking about a wave at the end of a string. I'll tie that into a sound wave later. Let's say it's coming into some sort of a fixed boundary. Say it's just attached to a wall or something like that. So the wave will come in, and then when it reflects back out, what will happen is it'll reflect back out upside down of the way it came in. And this is because if we look carefully at what's happened at the wall, as the wave is coming in, the string is tugging on the wall up, which means that by Newton's third law, the wall would have to tug down equally as hard. So this has the effect of snapping a new wave, propagating back upside down of the original. Now the situation is different if you have what's called a free boundary. So say if we have our wave coming in, and let's imagine that we've got like a rod and that we've got something that's allowed to slide freely up and down the rod. Then if a wave is coming in, what will happen is we'll just be moving this up, and then it'll be the same difference as if we were snapping a new wave right side up. So the reflected wave will come back out right side up the same way it came in. When you go and take a look at electricity and magnetism and look at the propagation of light waves, you'll find that this is an application of what's called Huygens principle. So what happens, let's say, if I have a string that's fixed on both ends? Well, then what's going to happen is as you send a wave down, its reflection is going to come back, right? And then that's going to go and hit the wall and reflect back. And so these waves are going to reflect back and forth. Now, what will be the case is that for just some typical, totally random frequency, these waves will generally just interfere themselves out almost completely. And so you'll see the string maybe do just a very light buzzing around its equilibrium position, but nothing too special. However, if you play with this, for instance, if you have a slinky that you can play with or something like that, stretch the slinky in both hands and just start snapping it up and down on one of your hands, you'll notice that there will be very specific frequencies where you can drive it, where you get a very special pattern happening. And this is where the reflected wave constructively interferes with the transmitted wave. And this gets called, as a bit of a misnomer, a standing wave. So when you look at it, well, if I make a series of snapshot graphs here, the snapshot graph will look something like this. So at t equals 0, it looks like this. At a quarter of a period, the entire string is flat. At half a period of oscillation, we get the exact upside down of what we had at t equals 0, and then the cycle repeats. So at t equals 3/4 of a period, nothing. And then finally, after a whole period, we end up, in fact, my bad. After a whole period, in fact, I'll even just be cheeky about it and copy paste it. We end up with the exact wave that we had before. Okay, so time for a little bit of anatomy on our waves. So if we look at the waves, we'll see that there are certain points along the wave where the string never moves off the equilibrium position. These points get called nodes. And then there are other points where the oscillation is at an extreme. These points get called antinodes. Okay, as before, this entire distance here corresponds to one wavelength, and I'd say about half the books out there give as a special name to a half a wavelength, they will call it a loop. And this is because if you watch it oscillate, it kind of looks loopish. So what we've got is every single point on the string executing simple harmonic motion, and the size of the envelope it's allowed to oscillate in is itself dictated by a sine function. So that this only happens at very specific frequencies. So let's try to figure out what those might be. Well, it turns out that will depend on the boundary that you have. So the first case we'll look at is if both ends of the string are fixed. So for instance, any stringed instrument pretty much, a guitar, violin, whatever, this is what you'll have. The string will be tied down some way or other at both ends. And so because it's tied down there, it literally can't move. So you have to have a node here, and you have to have a node here. So let's say the distance between my two boundaries, my two supports, is L. Let's try to figure out the longest wave I could fit in here. Well, if I put in just one loop, the distance from one node to the next, that would do it. So we'll call this just example number 1, just so we can keep track of it. This turns out this will get called the first harmonic. Also gets the name the fundamental. So here, because there's just one loop, that's half of a wavelength. So we can rework that to get that the wavelength is 2 times the length of the string. Okay. Now let's go and take a look at the second harmonic. Well, the next thing I could possibly do is I could stick in 2 loops. So now we pick up an extra node right there. So in that case, here for wave choice number 2, this would be the second harmonic. So the length of the string would be 2 over 2, or just one entire wavelength at that frequency. So the second wavelength where we can have constructive interference will be 2 over 2 times L. Yes, I know I could cancel the 2's, but I'm looking for a pattern here. So I want to leave it in to make the pattern obvious. Well, what's the next choice we could imagine? Well, the next choice we could imagine is sticking in 3 loops, like so. So we'd end up having a node here and a node here, in addition to the nodes at the end. So then the third harmonic, we can observe there that the length of the string would be 3 loops at that frequency, and each loop is half a wavelength. So this would be 3 over 2 lambda 3, or we can work it out that lambda 3 has to be 2/3 L. And now I think we can start to see a pattern. The 2 always stays the same, the L always stays the same. What happens is we just keep sticking different integers into the denominator here for the allowed wavelengths. So our general case is that the mth allowed wavelength, the mth harmonic, so here m is not mass, it is just an integer, will be equal to 2 over m times the length of the string. So like I say, m is an integer, it's not the mass. So there we go. Now, we can use v equals f lambda to work out what the frequency would be, right? Because the frequency will be v over lambda. And so if I work that around, I get that the mth frequency that this thing would generate would be equal to m, and I'm going to write it as v over 2 lambda, like that. And the reason I do that is this is the fundamental frequency. So the second harmonic will be 2 times the fundamental frequency. The third harmonic will be 3 times the fundamental frequency. The fourth harmonic will be 4 times the fundamental frequency, and so forth. Okay, so that's the case if both ends are fixed. What if both ends are free to move? Well, if it's free, then what we're going to need in order to have the wave reflect back on itself without interfering is that we will need antinodes. At both of my boundaries. Because if anything else, what we'll be getting is sort of like a wave on the upside coming up, say, interfering with a wave coming down, and then eventually it all cancels out. So the only way that we can have the wave going out look exactly like it was coming in is if we have an antinode there. So all right, so we can play the same game. So for instance here, I can stick in one loop. Going from one antinode to the next is still half a wave. Then my next case would be if I had 2 loops. See here, antinode, antinode, antinode. Then the next case would be if I had 3 loops. So then antinode, antinode. So it's, other than that, I think I mismatched the colors. Yeah, I did. It's the exact same relationship that we had before. So it turns out that all the equations we got, if both ends were fixed, apply if both ends are free. Where things will be different is if one end is fixed and one end is free. Now this is really hard to do with a string or something like that. The best I can think of is try to take a chunk of a jump rope and let one end dangle, and you can try to wiggle the jump rope. That's about the best that I can come up with. But for sound waves, certain shaped pipes are very straightforward to make one end fixed and the other end free. So if that's the case, we're going to need, on the fixed end, a node, and on the free end, we're going to need an antinode. So let's go think about the fundamental. Well, the longest wave I could possibly pack in, if this distance is L, would be half a loop, a quarter of a wave. Just because if you look at the wave, it goes node, antinode, node, antinode, node. So this would be a quarter of a wave. So our first harmonic, the fundamental, we'll observe that the length of the string would be a quarter of the wavelength of the fundamental. So the wavelength of the fundamental would be 4/1 times the length of the string. All right, what's the next one? Well, the next one would be if I stuck in an entire loop and then a half a loop after that. So here I go node, node, there's an antinode here, antinode there. So for the second harmonic, I would have realized I stuck in 3/4 of a wave. So the wavelength of the second harmonic will be 4/3 the length of the string. Then the next possibility we could imagine would be, say, if I stuck an entire wave in and then ended an antinode. So there'd be an entire wave plus another quarter of a wave. So that would be my third harmonic. So there we'd say the length of the string was 3/5 of a wavelength, or sorry, 5/4 of a wavelength, because I fit in 5/4 of a wave. So the wavelength of the third harmonic would be 4/5 L. Okay, and now I'm going to present the general equation two different ways. Pretty much every book written in the last 20 years writes the general equation like this, which personally I find a little confusing, but I'm not going to argue because I know these things are focus grouped to oblivion. So this number here will go 1, 2, 3, 4, 5, because this is the harmonic number. And then over here, what they intend for you to do is to put in 1, 3, 5, 7, etc. So this is the first odd number, the second odd number, the third odd number, in order to fit the pattern, right? Because our pattern goes 1, 3, 5. So say if you wanted the fifth harmonic, you'd put in a 5 here, then you would count to the fifth odd number, 1, 3, 5, 7, 9, and you would stick in a 9 there. If you find that confusing, here's an alternate way to do it. So I'm expecting most of you will probably like this because this seems to be what the focus group testing in all the books likes. But if you look in older books, they would make the observation that there is an equation for the mth odd number. If you look at 2m minus 1, let's just take a look at what that gives you. If I put in a 1, 2 times 1 minus 1, that's 1. If I put in a 2, 2 times 2 minus 1 is 3. If I put in a 3, 2 times 3 minus 1 is 5, and so forth. So if you feel like you're going to have a hard time remembering to put in the mth odd number, you can instead choose to write it as 4 over 2m minus 1l. And here you would put in just 1, 2, 3, 4, 5 into both sides of the equation. Again, like I say, I expect that you'll probably find the boxed version easier because there's got to be a reason why every textbook in the last 20 years has gone to that approach. And similarly, we can use v equals f lambda to obtain that the frequency of the mth harmonic will be equal to 4, will be equal to m times v over 4l, for L. And this is the frequency of the fundamental. So again here, this is 1, 2, 3, and then this is the first odd number, the second odd number, the third odd number, and so forth. So it turns out that this is odd numbers times the fundamental. If you prefer the alternate way to write that, it would be Fm equals 2m minus 1 v over 4l, or times f1. And then on both sides you would put in that m is 1, 2, 3, and so forth. But again, like I say, I'm assuming that there is a really good reason why every book has done this for the last 20 years. So what if you have, so this can be done as a design feature. For instance, with sound waves, the way you get your standing waves when it's sound is if the end is closed. So say if you have a pipe where both ends are closed, that's the same difference as fixed. And if both ends are open, that's the same as both ends being free. And then finally, if one end is closed and one end is open, that's the same difference as fixed free. Now, if you've seen any presentation from acoustics, acoustics texts might make the exact opposite choice and say that closed ends correspond to free and open ends correspond to fixed. And this is because here I'm looking at a displacement node, and in acoustics books they're usually looking at pressure, and it turns out that a displacement node is a pressure antinode and vice versa. So in that situation we're both correct, but we need not particularly worry about that. So what that means is, for instance, when you're designing an organ, First off, to get the really, really low notes on an organ pipe, you'll often make one end will always be fixed because that's where the reed of the instrument is. Yes, technically an organ is a woodwind. If the pipe is open at the other end, that will make a wavelength that is 4 times longer than the pipe itself for the fundamental. Whereas if it's closed at the end, it'll make a wave that's 2 times longer than the fundamental. Now, places where you like having it closed is when the pipes get really short, because it's easier to make a bigger thing than a smaller thing. On the flip side, to get the really low notes with the really long wavelengths, having it be open at one end so that you can basically double the wavelength for the same length of pipe saves an awful lot of pipe. Now, in addition to that, though, the designers of the organs have to worry about the available overtones. So if both ends are fixed in an organ, you'll have harmonics that are integer multiples of the fundamental. Whereas if one end is closed and the other end is open, then you'll only have odd numbers times the fundamental, and you'll be missing the evens. So let's say if you're doing concert A, if both ends of the organ pipe are closed, the fundamental will be 440. There will be a second harmonic at 880, and then another one at 1320 hertz, and so forth. If the other end is open, then the second harmonic, there will be no harmonic at 880. The next harmonic will be at 1320. Now, the exact details of the choice of materials, the nature of construction, how exactly they saw little teeth onto it's usually a metal reed, but it could be a wood reed in the case of an organ pipe. How exactly they saw little teeth onto it, that is dictating the relative strength of each of the fundamentals. And so the unique combination of overtones gives rise to the unique sound. Okay, and with that, that finishes up this entire video series on introductory mechanics. If you've made it through this far with me, thank you so much for being on the journey with me, and I hope to catch you again at some point in the future in cyberspace. Have an awesome time. Bye.